This little machine could light a path that makes ITER obsolete before it even switches on.
That is highly hyperbolic. It's time for some more mega projects. Specifically, will this change energy? This is Spark, or MIT's attempt at fusion. Well, even if it does work, probably not as fast as a lot of people would think. For those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer, a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I'm close to everything there is nuclear, but I can certainly share some knowledge.
If you wanted to build a fusion reactor 10 years ago, the logic was simple. Make it really, really big. The bigger the machine, the larger the plasma volume, and the easier it was to confine superheated gas long enough to achieve sustained fusion. That's why the world poured billions into ITER, a project whose main construction platform is so large it takes up the space of 60 soccer fields.
So a bit of context here. So yes, historically, the path to fusion appeared to be large, low-frequency, high-volume devices such as the tokamak, has been the large, low-frequency, high-volume tokamak. There's also the stellarator approach, but tokamak in the case of ITER, or ITER as you just said. And that's because larger machines give longer confinement time, which is more margin to achieve fusion, which you need confinement time, high temperature, and high pressure. Also seen high pressure referred to as density. As density when you look at the Lawson criterion, but it's the same idea. But yes, this design, this experiment, intentionally traded size for more forgiving margins. Now there's been other approaches as well, but tokamaks extrapolated well, so they were trying to build something that's more at scale. The goal's 500 megawatts with ITER, but overall, yeah, that's the basic idea.
Which I believe is about the same as 60 American football fields, but I'm not sure. But then came a group from MIT who basically said, what if size isn't the answer? What if we do something else? And their proposal was a machine called Spark that was barely the size of a room. And they claimed that this machine could achieve net energy from fusion, something ITER's gargantuan monster has not achieved yet. It sounds almost ridiculous. For decades, every fusion model said you needed vast magnetic fields, kilometers of supercooled coils, and mountains of shielding. But Spark doesn't have any of that shit. It's small, it's fast to build.
Alright, so like any other engineering choice, they're just picking different constraints. It's not magic, it's using similar principles that ITER used. They're just using different trade-offs. It's a redesign that trades magnetic field for size. It uses high-temperature superconductors to make much stronger magnets. So they're trying to get the plasma confinement of a much larger machine in a smaller volume that way, which is a real shift that is important, but doesn't remove the hard engineering and materials challenges associated with that. But this isn't the only one. There's been other alternatives, pinches, stellarators, spheromax. This isn't the only group to try something other than ITER. And then there's inertial confinement fusion, such as the National Ignition Facility.
And there's a chance it might work. The trick is in the magnets they're using, you see. A new generation of high-temperature conductors that are strong enough to shrink an entire fusion reactor without changing the underlying physics. If MIT is right, this little machine could light a path that makes ITER obsolete before it even switches on. And
whoa, okay. That is highly hyperbolic. Assuming Spark reaches net energy fast, that would again be a milestone, but ITER's goal isn't commercial power generation. It's a really big science experiment. It focuses on long pulse burning plasma science, blanket testing, international collaboration, and material validation. Spark is a compact demonstration of high field engineering and net energy impulses. Now, if Spark were to succeed, it's not going to instantly make ITER irrelevant. ITER still addresses different validation questions such as material irradiation concerns, sustained operations, and integrated systems that you would get from working at a larger scale. Just like within fission, boiling water reactors did not make pressurized water reactors obsolete. Both of them are used.
Why size used to matter? Fusion sounds simple when you say it out loud. Take two light atoms, usually forms of hydrogen, smash them together hard enough and you get a burst of energy. It's the same process that powers the sun, which makes it almost poetic. Imagine just the ability of creating a wee little star on Earth. But the reality is, stars have a massive advantage. They've got a lot of gravity because they're really big. They've got enough gravity to squeeze matter at millions of atmospheres of pressure until atoms just can't resist merging. We don't.
That's one of the reasons why you can get away with temperatures that are relatively cold. 15 million degrees Celsius is cold compared to the ones we have to do on Earth, which are upwards of 100 million degrees.
Have that kind of force, so we have to cheat to get the same result. In our case, we use an absurd amount of heat. And we're talking roughly 100 million degrees Celsius. That's 6 times hotter than the core of the sun. And when you try and trap something that hot in a machine made of metal, it's like trying to hold jelly inside a cage made of rubber bands. It wants out in every direction. So physicists came up with a workaround. Magnets. Really, really strong, powerful magnets.
See, in there he's showing a stellarator as well. So, yeah, more than multiple methods with different approaches here.
They twist and confine the plasma, that soup of charged particles, into a shape that never touches the walls. And the idea became, well,
really the emphasis on the twisting is with stellarators.
The bigger the reactor, the longer you can hold their plasma stable. That's where the Lawson criterion comes in. It's a sort of recipe for fusion, and according to it, you need 3 ingredients in the right balance: temperature, density, and confinement time.
Okay, you got that part right.
You can raise any one of them to make fusion work, but if confinement time is short, you have to make the other 2 extreme, which is why for decades the only answer was to make the reactors huge.
He's being a bit absolute here when saying every. I mean, there are exceptions, such as, again, stellarators, accelerator concepts, spherical tokamaks, all of which have looked at the size trade-off before.
That's how we ended up with ITER, a monstrous donut-shaped tokamak being assembled in southern France. It's over 30 meters tall, weighs as much as 3 Eiffel Towers, and when it's done, it'll be one of the most complex machines ever built. The logic is, with a bigger volume and longer confinement period came a higher chance of hitting.
As far as complex, yes, you can argue it's more complex than a nuclear power plant, at least as far as how the reactor operates. Because, again, here you're not even connecting it to the grid or anything. Because you're dealing with 2 extremes, extremely hot temperatures for the plasma and extremely low temperatures to achieve superconductivity. You're not that extreme in either direction for a fission reactor.
The ever-elusive break-even point where fusion puts out more energy than it takes in. But the thing is, as fusion devices get bigger, they also get slower, more expensive, and harder to build. Projects that started with a 5-year plan are running into 30 years with no end in sight. If you look back, fusion history reads more like a cycle of hope and frustration. In the 1950s, there were Z-pinch devices, the first attempts to compress plasma with electric currents.
Okay,
they produced
so he is
a lot of
acknowledging these,
enthusiasm, but also a lot of instability. The plasma would twist, kink, and escape, ruining the confinement. Then came tokamaks, which the Soviets invented in the 1960s. These toroidal machines finally gave scientists something they could work with, and by the 1970s, everyone thought that we were 30 years away from practical fusion. Then the 90s rolled around,
20 years.
And, well, it was still 30 years away. By the 2010s, the same story. The joke became that fusion is always 30 years away, no matter when you are.
The number I've always heard was 20, but maybe, depending on where you live, there might be different levels of pessimism.
Ask. And honestly, you can see why. Fusion reactors got larger, heavier, and more expensive, but the physics didn't get easier. Holding plasma steady for seconds at a time was already a win. Getting it to self-sustain, though, that was where the problem was. But then in the last decade, instead of asking, how big do we have to make it so we can contain the plasma, some scientists started asking, what if we could build it smaller? And that question sounds naive at first, like suggesting you could build a jet engine out of a hairdryer. But it isn't as wild as it sounds. The key was magnets, specifically a new class of high-temperature superconductors, materials that can carry enormous electrical currents without resistance. Traditional superconducting magnets, like the ones ITER uses, have to be cooled with liquid helium and are limited in how much magnetic field they can produce, roughly around 11 or 12 Tesla. The new ones, based on rare earth barium copper oxide or REBCO tape, can go far beyond that, over 20 Tesla in some cases. That's not just a little improvement. In fusion physics, magnetic field strength has a huge impact. Because the energy confinement scales roughly with the 4th power of the magnetic field, doubling the field can make the reactor up to 16 times more efficient.
So that is a rough approximation, and it does show up in reviews of fusion power as a rough proportionality. But I want to clarify that it's not a law of physics, not an explicit law of physics such as the inverse square law or the square cube law or anything like that. That being said, it does emphasize that, yes, if you have much stronger magnets, you could shrink the reactor size and get more power out of it. But again, it's a scaling heuristic. Actual performance is also going to depend on things like plasma current, shaping, density, confinement mode, impurity levels, physics of the edge of the plasma. So it's useful for a rough rule of thumb, but there are other things that scale non-linearly with size.
So suddenly, you could achieve the same conditions in a machine that's half the size. And that's how Spark was born. MIT and their startup spin-off Commonwealth Fusion Systems decided that if you can make stronger magnets, you can make smaller reactors, and you don't need a $50 billion project to get there. Smaller means faster construction, lower cost, and the ability to test and iterate. It's fusion thinking turned inside out, and that's what's so interesting about Spark.
That's true with anything smaller. You can see that with small modular reactor design in the case of fission. And you can even adopt some agile project management and develop practices, which is kind of unheard of in the case of anything construction related, but you're closer to that when you get smaller. So you can go from R&D to coil fabrication to testing phases faster, but faster doesn't necessarily mean easier. Constructing all the coils, cryostats, vacuum vessels, it's still going to be heavy engineering. There's no getting around that, but what it does have is this rapid iteration is useful for learning. So they can figure out everything broke with it faster and shorten the cycles. But ultimately, fusion still demands rigorous testing, rigorous regulation. This is still the Nuclear Regulatory Commission we're talking about. Yeah.
It's not a wild new physics concept or a miracle material from nowhere. It's an engineering insight that challenges decades of scale-based dogma. The test that proved a new path. The breakthrough happened on September the 5th, 2021, at a nondescript lab on Albany Street in Cambridge, where scientists had spent half a decade trying to refine the Rebco tape into coils that could handle stress strong enough to crush steel. You see, a 20 Tesla magnet is more about control than it is about strength, so if too much current is pushed too fast, the material burns itself out.
You can have very high Tesla numbers. You just ask Styropyro and all the things that have fallen apart. But yeah, all about making and holding at a design load without some sort of catastrophic quench happening, which isn't the same thing. This particular test wasn't the same thing as a fusion reactor by itself, but it shows that, hey, we can make magnets that are big enough. But it doesn't tell you anything about plasma performance, fuel cycles, or endurance in a neutron-rich environment produced by deuterium-tritium fusion.
The test they were running was a balancing act between physics and engineering, and failure would have meant never achieving the smallest possible arc. In the control room that morning,
You can argue any sort of test is a balance between physics and engineering, whether it be destructive or not.
Engineers ramped up the current one step at a time, and as the magnet began to hum, instruments tracked temperature, vibration, voltage, anything that might hint at instability. And then it happened. The readouts crossed the threshold to 20 Tesla. Dennis White, the director of PSFC, later said that when they hit that milestone, quote, "you could feel the future shift." And he wasn't exaggerating. This was the strongest magnet of its kind ever built, one capable of shrinking a reactor tenfold while keeping the same confinement performance. You have to remember what this moment represented. For 70 years, fusion's biggest limitation wasn't theoretical. We knew the equations. We understood how plasma behaves, at least well enough to model it. What we didn't have was the ability to actually build a system compact and efficient enough to be practical. That's why the success of this test was such a breakthrough. It proved that it was possible to engineer the impossible. The team had designed this magnet as a single module in what would eventually be a full toroidal set for Spark. Each coil was made from hundreds of layers of Rebco tape, wound under incredible tension and cooled with supercritical helium. By the end of the test, the magnet had already stayed at full field without quenching once, and suddenly there was a new possibility in the world of fusion. As one would expect, the investors came trooping in. Within months, Commonwealth Fusion Systems had raised over $1.8 billion in new funding, one of the largest private investments in energy history, from backers like Bill Gates, Google, and several major energy firms. To put what they achieved in perspective, you'd want to imagine if you could take a particle accelerator the size of the LHC and build it on a single campus, or a supercomputer that used the same physics but fit on a desk. That's the kind of paradigm shift that we're talking about here. And the scientific community knew it.
Yeah, but all those have different goals in mind. And look, not to dismiss the 20 Teslas for their magnet performance. I mean, that's huge, but I don't know. I don't like to be the dream crusher with this guy, but there's a fair bits of leap in logic that, hey, getting a cool magnet's awesome, but that doesn't by itself get you a fusion reactor by the 2030s.
Even
that's connected to the grid and anything. I'm not sure what they meant by that, if they meant Q greater than 1 or grid connection.
Critics of private fusion companies, people who'd spent careers working on ITER, admitted this was a genuine achievement. The old debate about whether smaller high-field reactors could ever rival larger-scale ones suddenly had experimental data on its side. But there's something else about this story that often gets missed. The success wasn't just about Rebco or engineering, it was about culture. The Spark team was a blend of MIT researchers and private sector engineers, a hybrid model that felt more SpaceX than a university lab. They iterated fast, failed quietly, and didn't wait for international committees to vote on the next step. It was
all right. I mean, look, I get the idea and the image is great. I mean, as far as, hey, a bunch of people that are just going to nuke it out, pun intended, rather than waiting on dealing with construction delays, international approvals, all this sort of stuff. But it's still physics that you're up against.
Fusion research, stripped of bureaucracy, and it showed that small, focused teams could compete with billion-dollar international projects. That's part of why
they have different goals, and this is still a billion-dollar project. You just mentioned they're getting billions in funding.
The industry's momentum shifted almost...
I mean, sure, it's less than what ITER's getting, but I don't know. The imagery's kind of weird here.
Overnight. For White and his team, though, the work was just beginning. They didn't celebrate for long, because that 20 Tesla coil was only step one. The next challenge was to actually use it to build Spark itself, link those magnets into a toroidal configuration, and see if the plasma would behave as the models predicted. The machine that's trying to rewrite fusion. Spark, which is short for smallest possible, affordable, robust, compact, by the way, is MIT and Commonwealth Fusion Systems' answer to 70 years of frustration. Now, on paper, it's a tokamak, just like ITER, but in practice, It is a completely different philosophy. Instead of trying to build the most perfect machine possible, Spark is trying to build the smallest viable one. Spark Central Chamber.
Okay, now that's, again, going for a different sort of goal here, whereas, a more pure science facility that's trying to figure out the materials, the energy production, that sort of thing that you would see at ITER, but whereas this one's goal is to eventually get something out on the grid. Why not mention its actual competitors, such as Helion Energy, or General Fusion, or Zap Energy, or anyone else with a similar goal?
Donut that holds the plasma will stand only about 3 meters tall, with its plasma tube radius of roughly 1.85 meters. Compare that to ITER's 6.2 meter radius and 30 meter height, and you start to see the difference. Spark could fit comfortably inside of one of ITER's assembly halls and still have room to spare. But despite that size difference, Spark's magnetic field will be twice as strong. Those 18 high-temperature superconducting HTS coils built from Rebco tape will generate magnetic fields exceeding 20 Tesla, enough to squeeze plasma at pressure hundreds of millions of times greater than Earth's atmosphere.
Okay, at peak. You don't want to keep it running at 20 Tesla. The actual is probably going to be something more like 12, which is still higher. But the 20 is more of what it's rated for. It's kind of like the reactor coolant system at a nuclear plant was hydro-tested up to well over 3,000 psi, but operating pressure is at 2250. Same general idea.
The goal is to achieve a fusion energy gain factor, or Q, greater than 1. That means producing more energy from fusion reactions than the machine consumes to sustain them. Spark's design aims for Q10, 10 times more energy out than in.
So that number right there, that Q of 10. So first off, what that actually means is 10 times in plasma. That is to say, more fusion power than input heating power within the plasma itself. That's not Q total. That is to say, to run all of its auxiliary systems as well with that heat load. And it's certainly not how much is going on the grid minus house loads. And the nominal case for this is really something more like Q greater than 2. I have heard this 10 number. I'm pretty sure I know what source that he got it from as well. It assumes good confinement scaling and other favorable assumptions. I mean, but look, it's a demonstration device. If you get Q greater than 1, that would still be good for a demonstration device like this. But Q10 guaranteed, or you get your money back? No. The device mentions Q greater than 10, that once you start operating this thing, then hey, maybe if everything works well, we can get Q greater than 10. Which is not unreasonable for something at this stage of development to say something like that. And all in all, they're a bit more forthcoming with their design than other groups like Helion Energy and their claims of having fusion reactors to the grid a couple of years ago. And then this year, and then a couple of years from now. If you want to hear more thoughts on that, please look at the pinned comment.
To put that in perspective, the best tokamaks in history, like Jet in the UK, managed a Q of about 0.67. ITER, once complete, hopes to reach Q10 as well, but not until the mid-2030s. Spark aims to do this before the end of the decade. Now, that doesn't mean there's going to be a power plant. Spark is a demonstration device. It's designed to prove that compact, high-field fusion can be achieved. The next step after that is ARC, a larger, grid-connected version that could continuously generate about 200 megawatts of electricity. ARC will reuse Spark's magnet technology, but add the systems needed to actually extract heat, drive turbines, and feed power to the grid.
Yes, you're going to want to use something else for that, and yeah, that's what they're showing. And that's, again, reasonable. Like, when you think of the days of the first fission reactors, the first ones didn't make electricity. And this would be more of a pilot plant rather than a grid-scale plant after, assuming all goes well with your demonstration device. But each step is going to introduce new engineering challenges, such as continuous operation, tritium breeding, remote maintenance, component damage and replacement under high neutron flux, not to mention supply chain and economics. And the range of this, 200 to 400 megawatts, which, again, not bad for a pilot plant.
It's a remarkably pragmatic roadmap. Instead of one gigantic leap, MIT and CFS are taking 2 deliberate steps. First, show the physics works, then scale it into a working power plant. And they're doing it fast. Spark's construction began in 2023 at Devens, Massachusetts, an industrial site about an hour from Boston. The plan is to complete assembly by 2025, achieve first plasma around 2026, and aim for net energy demonstrations soon after that. If that happens, Spark could beat ITER to break away by nearly a decade at a...
So if he's talking strictly Q greater than 1, then yes, that is plausible as a timing statement. However, I say again, ITER is a huge international project designed to demonstrate burning plasma regimes in a way that's conservatively engineered and political. It has massive schedule and integration complexity, and it aims for long pulse operations and tests, compared to something compact, high field, and short pulse demonstration, which is easier for short pulses for Q greater than 1. And again, it would still be a major scientific result, but to say that makes it better, then it's just not apples to apples.
Fraction of the cost. ITER, the world's largest scientific collaboration, involves 35 nations and a price tag north of $50 billion. Spark's estimated budget, by comparison, is under $3 billion, raised almost entirely from private investors. Technically, Spark is still a tokamak, a toroidal chamber where plasma is shaped and confined by a combination of magnetic fields, the toroidal field from the main coils and a poloidal field from auxiliary systems. But nearly everything about it has been rethought. Its magnets are modular, meaning each core can be removed or replaced without dismantling the entire reactor, a small but transformative feature that could save years in maintenance. Its cooling systems are simplified because HTS materials operate at higher temperatures, around 20 Kelvin instead of 4, allowing the use of supercritical helium. Even the structure itself is lighter and more compact, meaning future versions could be built faster, maybe even mass-produced.
All right, big leap in logic with the whole mass-producing things. All right, on the subject of cooling, so every deuterium tritium tokamak, such as this one, is going to produce neutrons and a concentrated heat flux at the plasma scrape-off. And this figures out to tens of megawatts per square meter in hotspots. That's going to be one of fusion's biggest engineering problems. I mean, you don't want hotspots in any type of reactor design. And smaller devices are going to concentrate power into smaller areas, which raises the surface heat flux and thermal stress on anything that faces the plasma. Now, and the diverter for that is a major focus area that they're working with, because the failure modes are going to look like damage to the vacuum vessel, contamination, and long outages.
The roadblocks ahead. Now, for all the excitement, there's a quiet understanding among people close to Spark that this could still fail. Spark is pushing the limits of control. Its plasma will reach over 100 million degrees Celsius, 10 times hotter than the core of the sun, contained inside a...
Though that part's the same order of magnitude as any other tokamak, but maybe he's going to get at the challenges with it being small.
Magnetic cage just a few meters wide. That's like holding a miniature star in your hands and hoping the walls don't melt. The smaller you make the reactor, the less margin there is for error. In ITER, there's room to absorb fluctuations and distribute heat. In Spark, a small wobble in the plasma could mean a full shutdown. Every microsecond of instability has to be corrected in real time with control systems that react faster than human perception. And then there's the question of magnet durability.
Sure, the stability margins are going to be tighter, and it's going to be on the order of microsecond as how these control systems operate. Because any disruptions could put huge electromagnetic or thermal loads in spots where they're not needed to be.
High-temperature superconductors, REBCO tapes, are what make Spark possible. They can generate magnetic fields nearly twice as strong as ITERs while staying compact and efficient. But they've never been exposed to a real fusion environment before. Usually, when deuterium and tritium fuse, they release high-energy neutrons that slam into the reactor walls and components.
14 MeV is a lot for a free neutron. To give you a sense of scale, a typical fission reaction, the neutron's going to have maybe 5. And that extra energy is going to mean a lot for things like neutron embrittlement and it causing long-term degradation of reactor components.
Over time, that radiation can damage everything it touches: metal, insulation, even the superconducting layers themselves. If the REBCO coil
and the fusion reactor vessel and its subsystems are a lot more sensitive. Because fission reactor, you just need a big pressure vessel. Worst thing you have to worry about there is just neutron embrittlement over the course of decades. Here you got a lot more sensitive electronics and magnetic things that are more susceptible to neutron embrittlement over time.
Coils degrade under bombardment, performance would drop. Repairs won't be simple either because these magnets are tightly wound and cooled. Replacing one could take months and millions of dollars. No one yet knows how long they'll last under real fusion conditions.
And that's a real concern with any operating fusion reactor. So more vulnerable systems and higher energy neutrons compared to fission. Some designs just focus on saying, okay, we know these things are going to break, just try to get them as cheaper and modular as possible. And essentially it's going to be a big waste product, broken magnets and coils.
And the only way to find out is by building and running Spark. Another major challenge is heat exhaust. It is one of fusion's most unsolved and underappreciated problems. Every fusion reaction releases energy in incredible localized heat where the plasma meets the machine's inner walls. Diverters, the specialized components that handle the exhaust, must manage heat fluxes higher than those inside rocket nozzles. If the diverter fails, the entire vacuum chamber can be damaged beyond repair. Large reactors like ITER are already struggling with this. Spark's compact design makes it even harder. The smaller volume means heat builds up faster, and there's less surface area to spread it out. Engineers are exploring new materials and cooling geometries, tungsten tiles, liquid metal layers, advanced alloys, but none of them have been proven at Spark's power density yet. And even if Spark's plasma performs perfectly, the fuel itself introduces its own complexity. The deuterium-tritium mix that powers most fusion designs is potent but delicate. Deuterium is easy to extract from water, but tritium is rare and radioactive, with a half-life of just over 12 years. Most of the world's supply comes as a byproduct of heavy water nuclear reactors in
which is why, hence the needing to breed it with lithium.
Canada and South Korea, and only a few kilograms of it exist globally. Handling it requires specialized containment and...
The problem with the few kilograms, so you can make that argument about uranium-235 during the days of the Manhattan Project. Not much uranium-235 existed, because they didn't need it for anything. So a new economy and logistics system around the ability to breed.
Licensing that can slow progress for years. Spark will consume small amounts for its tests, but any commercial follow-up will need a sustainable tritium cycle to breed new fuel as it burns the old. That's an entire subfield of research that's still largely theoretical. Without it, fusion just can't scale. Then come the regulatory and logistical hurdles. There's no established framework for licensing a private fusion reactor in the US because no one's ever built a fusion reactor that produces significant power. Spark's developers are working with the Nuclear Regulatory Commission to chart new ground, a process that could be as slow as the engineering. And yet, for all those obstacles, Spark doesn't need to clear everyone to matter. Even if it never achieves full Q greater than 1, the data it produces will be priceless. Validating the physics of high-field compact reactors would shift the entire field's direction.
So if it does work, what could change quickly is there would probably be more private and public high-field programs that want to capitalize on this opportunity. But things like tritium breeding and supply chains, neutron hardening coils, plus all the industrialization and regulatory frameworks, and competitiveness, you need to scale this stuff, that would still take a very long time.
It would prove that smaller machines can reach the energy threshold that's eluded scientists for 70 years. If Spark falls short, it could still succeed in the ways that count. It could confirm the magnetic confinement models that will guide the design
just the 20 Tesla
the next
stuff,
reactor in line. It could reveal exactly where material fatigue sets in, or how to build better diverters, or how to stabilize plasma more efficiently. Those lessons are how real revolutions start. The people at Commonwealth Fusion Systems, they understand this better than anyone. Many of them have already spent careers chasing projects that never reached ignition. They know science is slow. So when they say Spark might hit net energy, they're not trying to boast. They're putting forward a hypothesis that will take years of debugging, retesting, and redesign to prove. Spark's team knows that they're building something that might not work, but they're also building something that must be tried. Every step forward, every test, every failure, every adjustment brings the dream a little closer to reality. And if that reality looks anything like the one that they're chasing, even the roadblocks won't matter much in hindsight, because the difference between impossible and inevitable has always been measured in persistence.
This was actually one of his more measured videos. Yeah, celebrate the magnet milestone, but keep expectations calibrated. Fusion has always been a sequence of breakthroughs, hard engineering follow-through, and roadblocks and setbacks. So the fact that Commonwealth is being more measured, even Simon's being more measured about his explanations, I have to say that's certainly welcome. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.